invariant subspace has an orthogonal complement, which is also an invariant subspace. Anyway, so we're going to discuss this for now. There's generalization of this for any semisimple Lie algebra, and this will be our first topic for this lecture. But before, let us give a couple of definitions, as always. So first of all, what does it mean for an element of a Lie algebra to be semisimple or nilpotent of an abstract Lie algebra? So an element X in some algebra G is called semisimple if we consider its image under adjoint representation, and this image happens to be semisimple. And similar definition for nilpotent. So an element is called nilpotent if adjoint X is nilpotent. And with such definitions, we have the following theorem. So this definition works for every Lie algebra, but we need semisimple for this theorem. So let G be semisimple. Then any X in G can be uniquely written in the form X equals XS plus XN, where XS is semisimple, XN nilpotent, moreover, we have the following, that XS commutes with XN. That was a part of matrix Jordan decomposition as well. And equals 0, sorry. So let me be more accurate in my writing. Such that XS commutator with Lie bracket with XN is 0, and for if you found some element Y in G such that Y commutes with X, so should Y is G is such that Y commutes with X, then it also commutes with semisimple part. So here's the statement of the theorem. Let's prove it real quick. All right, so uniqueness follows immediately from the uniqueness of the Jordan decomposition for matrices. Right, so first let's discuss uniqueness. So suppose I have two decompositions. X is xs plus xn, where these are semisimple and nilpotent, and x is xs prime plus xn prime for some other semisimple and nilpotent xs prime and xn prime. Then let me take add x, right? It will be written as add xs plus add xn, and at the same time it's add xs prime plus add xn prime, right? Add is linear, of course, so we have this. But this is semisimple as a matrix, as a linear transformation. This is nilpotent. So this is a Jordan decomposition for this linear transformation. And this is a Jordan decomposition for this linear transformation, right? So therefore, add x s is add x s prime in particular, right? But from this, it follows that xs equals xs prime. Why is that? Yes. Joint representation is faithful because G is semisimple, right? xs equals xs prime because G is semisimple. Well, because this, of course, xn equals xn prime as well. All right, so uniqueness is easy. For existence of such decomposition, we will use the fact, the trick is to use the fact that derivations of semisimple Lie algebras are only inner derivations. You had this problem in the seminar, so we'll discuss it today. All right, so let us, so existence. Right, so we need some technical calculations. So denote, let us denote, and we'll use this notation. So again, so let us fix an element x in G, right? So we will try to decompose it. So this, consider add x, and for any eigenvalue lambda of add x, denote by G lambda generalized eigenspace. So eigenspace means the space of all eigenvectors corresponding to this. Generalized eigenspace is that, so eigenspace means it is this matrix minus lambda I kills all vectors in eigenspace, right? So generalized means some power of this matrix kills the vector. Okay, so let me just write it down explicitly. It is union of kernels of such things. Add x minus lambda times identity on G to some power n. And we take union over all n right from 1 to infinity. So of course, if we consider just this kernel for some n, if n is like if m is greater than n, right? Then this kernel, corresponding kernels, one is inside another, right? So it's like that. And therefore, since my G is finite dimensional, right? This union is actually there exists some n, right? Such that this union coincides with just kernel of this in some power n, right? So I just need to take big enough n, right, to kind of have all this. Right, so this is, there exists, so in fact, this is just some linear algebra. There is n lambda such that G lambda is kernel of add x minus lambda I to the power n lambda. All right. So we actually claim the following, that if I take G lambda, it's not a subalgebra, first of all, but it's some subspace, right? And I can consider still a commutant, right? This is another vector subspace. Makes sense, right? So I claim that this is inside G lambda plus mu. So let's prove this. Right. So my add x is derivation. Does everybody remember what is derivation? Or should I repeat? Okay. So derivation means that it acts by Leibniz rule with respect to some operation that we have on our set. So in this case, this operation is Lie bracket. All right. So in particular, the fact that add x is derivation is just the same as having Jacobi identity. All right. So the first observation is this, and all derivations I will denote like this. So I will use this, and then I can write the following. If I have two eigenvalues, lambda and mu, right? So if I take something like this, right, and apply to y z for some y in z and g, then I claim that this is add x minus lambda applied to y, bracket with z, plus add x minus mu. So then I take y without everything. And then add x minus mu applied to z. And I take a bracket. Okay, so look here. Is this clear? So I just used the linearity of the bracket, right? So first I applied add to bracket, right? It is add applied to y plus y add applied to z. This is just Leibniz rule and add is derivation. Then then I have term minus lambda times this commutator. I can put this lambda in front of y or in front of z. Doesn't really matter, right? The commutator is linear. So I put it in front of y. And so that's how I get this term. But mu I put in front of z. And this is how I got this term. Okay, now repeating this. So I can now apply again an operator of such kind again and again. So I can repeat this and get some kind of Newton binomial formula. Let me write it down. So applying this formula n times, we get. So I would like to see what is add x minus lambda minus mu to the power n applied to yz. So I claim that this is sum over I from, or maybe k, from 0 to n. And then I have binomial coefficient and choose k, and then I have add x minus lambda to the power k applied to y, comma add x minus mu to the power n minus k applied to z. So this is just the same combinatorics as in Newton binomial coefficient, right? So I take this, have these two terms. Now I apply this again, so I can apply add x minus lambda minus mu to here or to here. I will have 4 more terms, and so on. But I will have 4 more terms, but 2 of them will be of the same kind. So I will have 3 terms, but with some coefficient, 2, right? Which is this binomial coefficient, and so on and so forth. All right. So I will use this to. Now let me take y and z. Y is from g lambda, and mu is from z and from g mu. So let's take y from g lambda, z from g mu. Then what happens? And I would like to take n, this n, greater than n lambda plus n mu, where these are my n lambdas and mu's. In any case, so if I apply this in the power greater than n lambda to y from g lambda, this will be 0, right? Or if I apply this to the power which is greater than n mu to z, which is from g mu, I will get 0. So I claim that in each of these terms, it's either this term, I will have here something greater than n lambda, or here I will have something greater than n mu. Because the sum should be equal to n, but n is greater than lambda plus n mu. All right? Then our formula just gives that add x minus lambda minus mu to the power n applied to yz is 0. But that's exactly what we wanted. So this is our claim, right? It means that if I take a commutator of 2 things from these 2 subspaces, I get something which is killed with this eigenvalue, which is lambda plus mu, to some power n, right? So claim follows. Now let us apply this claim. So we would like to to see that, so let me take now add x, and I can decompose it as add x semisimple part and add x nilpotent part. This is just usual Jordan decomposition. Let me now, so the goal is to prove that this thing is a derivation on G. Therefore, I will have some xs such that this is add xs, right? So how to do that? Let me take, so first observe that add x so since lambda is some eigenvalue of add x, right? And semisimple part has the same eigenvalues, right? And therefore, G lambda actually is an eigenspace for a semisimple part, okay? So therefore, this is just lambda times identity on G lambda. It's just multiplication by lambda. I'm using this. Let me take, again, y from G lambda and z from G mu. All right. And then let me take add x s and apply it to y z. Right. So what do we have? We have the following. So first of all, from the claim, this thing lives in lambda plus mu, right? So therefore, and we have also this. So therefore, this is just lambda plus mu or multiplied by the same thing, y and z, right? Then I can take this and write it like this: lambda y with z plus y with mu z, right? This is some number. I can either multiply y by this number or z by this number. So I can multiply lambda by y and mu by z. So these are two terms. But this is the same as add x applied to y z plus add x s only, right? Because y lives in G lambda, but add x, application of add x to anything from G lambda is just multiplication by lambda. So this is what happened here. So, and plus, just the similar argument, y add x s applied to z. Okay. Since we have, the sum over all eigenvalues gives us, so actually our G, right, is a direct sum of G lambdas, right? Because if I have like a matrix, right, I have decomposition into generalized eigenspaces of my vector space, right? So this is another fact from linear algebra. So we kind of checked on some elements of the subspaces, but since all these this subspace spans all G, right? We checked that actually add XS is a derivation. Is this clear, or should I repeat? Should discuss more?
I just have a question.
Sure.
In this part, when you were saying that if you have an eigenvalue or eigenvector in the whole matrix, then
Right.
the semisimple part preserves.
Yes.
Why is this so?
So you're asking about this, right? So think of matrix in Jordan normal form, right? So you have some lambdas, right? Blocks like this. Then just consider consisting of one block, right? So in this case, the whole space is just generalized eigenspace with eigenvalue lambda, right? So just one eigenvalue, and you have Jordan. Then semisimple part of it is just what? It's just this, right? So this is just lambda times identity. So that's why. In the same way, so if you have two blocks, say like this, lambda and say mu, right? Then if I restrict, so what's written there? I restrict to G lambda. First I take S, right? When I take S, it is just diagonal matrix like this. But then I would like to restrict to G lambda. I restrict to G lambda is just this block. So this is a lambda times identity on G lambda. So that's how it works. Of course, I'm working in some particular basis. Here, maybe you should have to conjugate and do all the stuff, but that's actually what happens. Yes, any other questions? Yeah, so you see here I took some particle, that's one thing that might be not clear. So here I took some particle y and z, right? And for them, I have, I'm sorry, that's like that. For them I have that this thing operates by Leibniz rule, right? For some particular. But if I take any x from G, right? It just can be written as a sum from elements from G lambda 1, G lambda 2, and so on. And then I prove that this is actually a derivation by linearity. Okay. Very well. So this derivation, let me erase that. But this is the same as inner derivation. This is because my G is semisimple. We didn't prove it yet. We almost proved. We kind of discussed indirectly the proof, because I mentioned that the homology of Lie algebras are related to the proof of complete reducibility of finite-dimensional spaces. So that's actually so the clue point to get from the point where we were in the last lecture to actually a general case of complete reducibility is to prove that the first cohomology of Lie algebra is 0. But actually, the first cohomology of Lie algebra is the quotient of derivations by inner derivations. That's how they work. So we indirectly kind of discussed that last time, right? Yes, so we also have the problem from seminar. Right? So, anyways, but I would like also to notice that it's related to complete reducibility as well. All right, so you have this. Then it means that add x s is add x s for some element x s in G. Right, that's what it means. That x s is in an inner derivation. It's in the image of add. Right. But what we know about this element? This automatically means, so this is semisimple part, right? So therefore, this thing is semisimple. So therefore, automatically this means that xs is semisimple. Well, how to define n? Of course, I would like n to be x minus xs. And I would like it to be nilpotent, right? So let me take add xn. This is add x minus add x s, right? And this is then add x minus the semisimple part of add x. But this is nilpotent part of add x. Right? But so therefore this thing is nilpotent. And by definition xn is nilpotent. Xn is nilpotent. So we have existence now. We just need to prove that they satisfy these conditions, right? But again, now everything follows from the abstract Jordan decomposition. So if we take add, so if we take add xs xn, add of the commutator. Okay, this is homomorphism of Lie algebra, so therefore it is add x s commutator with add xn, right? But this is the commutator of semisimple part of add x and semisimple part of add x and nilpotent part of add x, right? So write this. But this is 0 from just usual Jordan decomposition. Image of the adjoint map is 0 of a commutator. But this means that this thing is also 0 again, because the center is trivial in a semisimple Lie algebra. Right, so therefore, xs and xn is 0. what else should we prove? Right, so if we found y in G such that, so suppose y in G is such that y with x is 0. Right. So then again, we would like to prove that y with xs is 0. So let's see. Maybe we can again take y of this, right? So this is add y at xs, right? So how to do it? Yes. So maybe let us do the following way. So if we found y such that this happens, it means just let's rewrite. So okay, this I will not need. So let me just rewrite this as follows: add x applied to y is 0. It just means that y is an eigenvector of add x with eigenvalue 0, right? Well, of course, I would like this not to be 0. Well, for 0, it's trivial, right? Of course, this also follows, but let's take non-zero y. So therefore, y is eigenvector of add x with eigenvalue zero. But this means add x s. It has the same eigenvalues and eigenvectors, right? Not the well, eigenvectors of y are eigenvectors of add x, eigenvectors of add x s, right? This guy has more eigenvectors actually, right? So, but eigenvalues are the same. So this means that this is 0. But then this is the same as xs commutator with y is 0. Because this guy is at x of element xs. All right, so we proved theorem completely. Are there any questions? Okay, if not, then let's continue. So we introduced semi-simple elements, and they will be very important for studying semi-simple algebras. In particular, we would like to consider even subalgebras consisting of semi-simple elements, right? And moreover, so here's another definition that we will need. What is a toral subalgebra? A subalgebra H in G is called toral if it is abelian and consists of semi-simple elements. well, we'll be in particular interested in some toral subalgebras which are called Cartan subalgebras. But they have some additional property, but let us now formulate something which is true for all toral subalgebras. Okay, proposition. Okay, let me fix semisimple algebra, toral subalgebra, semisimple, H inside G is toral, and also let me fix some invariant non-degenerate symmetric bilinear form. Invariant, you can think of Killing form, but maybe I would like to rescale it somehow on a simple summons. I don't know. So invariant non-degenerate symmetric bilinear form. Then the following happens. First of all, G decomposes into some subspaces which are eigenspaces of our subalgebra G, but they are common eigenspaces. So this lambda, it lives in linear functionals on H, and G lambda is actually defined as follows. These are elements in G such that add H applied to X is lambda of H. This is some number, right? Times X. This is for every H in our subalgebra H. So this is the explicit definition of G lambda. It was generalized eigenspaces last time. So now these are eigenspaces, and they are common. So, but now we have a bunch of elements, right? So G lambda, now lambda is not a number. It's actually linear functional depending on which particular element, eigenvalue of each particular element we consider, right? And it is X is a common, if it lives in G lambda, it is a common eigenvector for all H's. And the corresponding eigenvalue is given by this number, lambda of H. All right. Second is that the following. Right, so actually I have G lambda with G mu is inside G lambda plus mu. This is just actually, these two are important to just formulate them, but they kind of follow easily from what we said already. Now, but we have other two parts in this proposition. Which concerns the form that we fixed. So number 3 says that if if my lambda and mu are such that lambda plus mu is not 0, then g lambda g mu, so g lambda and g mu are orthogonal with respect to this form. All right. So that's third statement, and fourth statement is that now if otherwise we have a non-degenerate pairing, right? So otherwise this form gives a non-degenerate or is a non-degenerate pairing, well, from where? From G alpha tensor G negative alpha to to C. So non-degenerate means that there's no element x in G in G alpha, right? Such that if I plug it into the first component of the form, or it's symmetric, doesn't really matter, right? If I plug it as one of the components to the form, then for all elements from G negative alpha, so there's no, let me write this down explicitly. So there is no x in G alpha such that x, y equals 0 for all y from G negative alpha. And symmetric statement, right? If I take, there's no x from G negative alpha such that this is 0 from all y from G alpha, right? So this is non-degeneracy. In particular, it means that this form gives an isomorphism from G alpha to G negative alpha. So their dimensions are the same. Okay, so this is the statement. Let us prove that. Sure.
Because here this toral subalgebra, it's in analogy with the H that we were working before with in the case of SLN.
Yes, it's diagonal, yes.
And in GL, just the diagonal matrices?
Yes.
And here, my question is if we have, like, in analogy with that, we have here a name for the subalgebras that are in the nilpotent part, like E and the E's and the F and the F's?
Yes, sure. These are G lambdas. Yes, so G, as a vector subspaces, right? Right, so you should take right, so it's you kind of looking forward, right? But we would like to claim that some of the lambdas are positive, some of them are negative, right? So if you take all lambdas positive and consider all G lambdas, this will be an analog of what you're looking at. Yes.
What is H star?
H star are all linear maps from H to C. Yes. Yeah, do. Yes. Did I answer your question? Yeah. So it's So if you take if you choose some hyperplane, right? It depends on the choice of H. Right, in H star, right, you can choose a hyperplane. such it doesn't intersect any lambdas. This lambdas actually is a finite set, right, of some vectors in H star. And then on one side of this plane you will have positive lambdas, on the other side negative. And then you take a direct sum over all positive. And this will be your E's, and the other ones are F's. Yeah.
So in the same way as before, then we are going to take the highest weights?
Yes. That's where we are moving. Okay. And in the same way as with SLN, as will be on the next lecture, we would like to find SL2 triples inside. So it will be some G lambda, something from G lambda, something from G negative lambda, and some element from H. Yes. Okay, very well, thank you. So let's prove it. Right, so there's really nothing, not too much to prove in the first two. So first one says that, okay, we have in H all elements are semisimple, right? And therefore they're diagonalizable. So I mean add X is so okay, let me write something. Add H is diagonalizable for all H, for all elements H in our subalgebra H. This is just because all these elements are semi-simple. And also they commute, because the H is abelian. Right, so also, and add H1 commutator with add H2 is 0 for every H1 and H2 from H. So therefore, if you have a bunch of diagonalizable matrices that commute with each other, you can simultaneously diagonalize them. That's a result, some standard result from linear algebra. Right, so therefore, at H, where H lives in our subalgebra H, can be simultaneously diagonalized. Can be diagonalized simultaneously. But this is exactly what the first one says, right? So it means that our subspace G, right, consists or it has a basis of common eigenvectors of add H. That's exactly what's written here. Okay? So one follows. Then this one we already proved as well, but we had for generalized eigenspaces. All right. It doesn't really matter that we proved that for just one element, right? So now so it works like by the same formulas for all of them, right? We're kind of now writing this nicely, all the eigenvalues, just using one element from H star, right, for all the elements there. So this one we already proved, but I don't want you to, go back and remember this computation, maybe. it just even easily follows from the by the following computation. So I just take add h, apply to yz, right, where y is from g lambda and z is from g mu, right? This will be, because add is derivation, right? I have add h applied to y z plus y add h applied to z. But then by definition, this just multiplication of lambda by y, and this multiplication of mu by z. So therefore it is lambda y commutator with z plus y commutator with mu z. So therefore it is just lambda plus mu yz. It's a very easy version of what we had in the proof of Jordan decomposition. So therefore we see that add h acts on such commutator by multiplying by an eigenvalue lambda plus mu. This exactly means the following thing. And what about 3? This is, for this one, we need invariance of the form. Right. So again, I take x from g lambda, y from g mu, and I have that lambda plus mu is not 0. Then for my form, I have the following: add h applied to x form with y is the same as right. So not the same, but it's plus x, and then form of x with add h applied to y. So by invariance of the form, this is just 0. Okay? This is because form is invariant. This is just definition of invariance of the form. We had this in a slightly different way, right? With commutator instead of add h, and maybe they was on different sides of equality, but it's just the same thing, just rewritten like this. Okay, x is from here, y is from g mu. Therefore, I have that this equals to lambda plus mu xy. Now this thing is not 0 by the condition. So therefore x and y, therefore this is 0. And that's exactly what I claimed in 3, right? If I take some element from g lambda, compute form with some element from g mu, it is 0. Okay, so number 4 immediately follows from the third one. And and from the non-degeneracy of the form on the whole G, right? So if it's degenerate on when restricted to this one, then it's degenerate everywhere. Because the only way for the form to be non-degenerate is to be non-degenerate here, because for all our other subspaces, we just prove that it is 0. Right, so let us write this down. So if I have this form and restricted to G alpha tensor G negative alpha is degenerate, then by part 3, this form is degenerate, and we have, and so therefore we have a contradiction. And this is the end of the proof of this theorem. Okay, very well. So now let me introduce Cartan subalgebra. So notice that G0 in our notations is a centralizer of H, right? So actually centralizer, let me recall, right? So if I have some subalgebra H, then centralizer of the subalgebra all elements in G such that add X applied to H, it is 0 for every H in H, right? But this is the same as add H applied to X is 0 for every H in H because of antisymmetry of the Lie bracket, right? And this is the same as add H applied to X equals 0 for every H from H, but this is by definition just G0. Yeah, by the way, this invariant bilinear form that on G gives me immediately invariant bilinear form on G0, which is right because of number 3. Of number 4, sorry, right? Because well, 0 equals negative 0. So on G0, tensor G0, we have non-degenerate form, which is a restriction of the form from G. Moreover, this G0 is a subalgebra. Because centralizer of a subalgebra is a subalgebra. This can be checked directly. Anyways, what I would like to do is to define some particular class of toral subalgebras. So a toral subalgebra H is called a Cartan subalgebra. If its centralizer, right, coincides with itself. Suppose that now I have a Cartan subalgebra, then I have the following decomposition. Right, in my decomposition that I erased in proposition, right, direct sum of G lambdas, I can just replace G0 with H, right, because they just coincide. And this is very important decomposition, which is called the root decomposition. And it gives the root system corresponding to Cartan subalgebra. So suppose H is a Cartan subalgebra. Then we have the following decomposition. G equals H plus G alpha, where alpha is from some set R. So this R is a finite subset of H star. What was the definition of this subset? These are all, so R is all lambdas from H star, right? Actually minus 0, such that G lambda is not 0. This is a finite subset because our algebra is finite dimensional, right? And we have this direct sum decomposition. So this R is called a root system corresponding to this Cartan subalgebra. And this thing is called a root decomposition. So the right, if we fixed some H, right, the root decomposition. And then if I take alpha from R, then G alpha is called root subspace. So now one of the most important tools is to study these root systems. Like we already had some pictures in the previous semester. So if you remember this picture with right triangles for like a representation theory of SL3. So this is a root lattice for SL3, right? But we will get there. But we have more root lattices, right, for other semisimple algebras. Okay, so since I would like to, ideally, I would like to have one-to-one correspondence between root systems and semisimple algebras. I didn't define what is an abstract root system without Lie algebra, right? But in any case, without even any understanding, I would like to at least have some Cartan subalgebras inside, right? If nobody tells me that actually some Cartan subalgebras exist, then we have nothing to talk even about. So maybe in the rest of the lecture, let us try to see that Cartan subalgebras exist in every semisimple algebra. This, the existence of Cartan subalgebras will follow from the following theorem. Let H in G be a maximal toral subalgebra. Then H is a Cartan subalgebra. Okay, to prove this theorem, we will need some statement about G0, about the centralizer, right? So to prove this, it's enough to see that the centralizer is toral subalgebra. The centralizer of such an algebra is toral subalgebra. Since it's maximal, the one that we chose, it coincides with its centralizer. Okay, so that's the idea how to prove that. To prove that, we'll need the following lemma. Lemma concerns G0. So if X, if I take, so lemma consists of two parts. First part is that, well, as I said, G0 is a Lie subalgebra, right? If I take an element in this Lie subalgebra, I can decompose, apply Jordan decomposition in two different ways. I mean, as an element of G0 and as an element of G, right? Actually, nobody guarantees that these two things coincide. But for G0, it is true. Okay, so, right. So let x equals xs plus xn be the Jordan decomposition in G0, right? In G, okay. Then xs and xn, they belong to G0. So that's exactly what I said. And second statement is that G0 is a reductive subalgebra of G. Okay, so let's prove the lemma. Okay, so for the first part, we will just need the following. So if I take so proof, if I take x from G0, right, it means that x with h is 0 for all h in my subalgebra, in my toral subalgebra, just by definition of G0, right? But this means that x, the semisimple part with h is 0, right? Remember this, the last condition that we had for the Jordan decomposition, right? If I found h such that it commutes with x, it also commutes with semi-simple part for all h in h. So this actually gives number 1, right? So therefore, by definition, then x. So this is 2 ways, right? So therefore, I have xs, h, xs is from G0. That's it. Right? And therefore, xn is a difference of x, and the xs is also from G0. So to prove 2, so let me consider the form, the following form on G0. I take x1 and x2, and this is just a restriction of Killing form on G to G0. So first of all, this form is non-degenerate on G0. Right? Because I proved that the restriction of the form to G alpha tensor G negative alpha is non-degenerate. Right? So G0 0 is equals negative 0, right? So therefore, so this form is non-degenerate. On one hand. On the other hand, this is a trace form for G0 corresponding to a representation of G0, which one? G, right? So on the other hand, this form is BV, where representation of V is G as a representation of G0. Sorry. Right? So we just applied adjoint. Right? We have adjoint representation of G to G. And we can restrict it to G0. This will be a representation of G0 on G. And corresponding trace form to this representation is exactly the restriction of Killing form to G0. So we have trace form, which is non-degenerate. Therefore, G0 is reductive. Okay, so now let's prove theorem. We proved lemma. Okay, so I start proving the theorem from the proving of the following claim. So claim. So again, so we are working in this setting. Add x. Well, add x in the algebra C of H, right, is nilpotent for every x from C of H. Okay, let's prove this. So proof of claim by contradiction. By contradiction. So suppose it's not a nilpotent, therefore I can consider its semi-simple part, and this will be not 0. So suppose semi-simple part of this is not 0. Right, but then this semi-simple part is add. We know from abstract Jordan decomposition, it's add of xs. right? For some xs in CH. And it is semisimple in CH. Right? And it is a decomposition of x. It corresponds to the Jordan decomposition of x in CH. But we just proved in lemma that this thing, the Jordan decomposition in CH and in G coincide. Therefore, this element is also semisimple in G. Right? So by lemma, xs is semisimple in G. All right, so we would like to contradict the maximality of H, right? So we are constructing some semisimple element that we would like to add and make a bigger toral subalgebra. That's our trick. So that's this element. So suppose we found and some not nilpotent, therefore we have some xs. Right. So first of all, we would like this to be not in H, right? To make the H bigger. Why is that? This is just because add xs is in ECH is not 0, right? So if it was in H, then of course it would commute with any element from the centralizer, right? Right. So if this should equality of this thing to 0 is a necessary condition for an element to lie in H. So therefore, this implies this. So this xs is not in H, right? And this not 0 because of our assumption. On the other hand, I would like to see that xs with H is 0. This is why this is true. This is because x in CH, therefore x commutes with any elements in H, right? Just by definition of the centralizer. But we know that if x commutes with H, then xs commutes with H, right? So this is because x commutes with H for every H in H, right? This follows from this one. So therefore, if I take my H, so I take my algebra H and add this element to it. This will be commutative subalgebra, abelian subalgebra, consisting of all semisimple elements, right? Therefore, it's toral. So this is toral. But this is contradiction. Contradicts to maximality of H. Because H is inside. So therefore, we proved by contradiction that every element of X, its add X is nilpotent. We actually proved that by Engel's theorem that C of H is nilpotent, right? So by Engels, by claim and Engel's theorem, C of H is nilpotent. But on the other hand, so it's nilpotent. In particular, it's solvable. Therefore, radical of C of H coincides with C of H. Right? It is C of H itself is solvable ideal in itself. So therefore, C of H coincides with its radical. But what we proved? We proved that C of H is reductive. G0 is reductive. It was a dilemma that I erased from here. G0 and C of H is the same thing. Reductive means that radical coincides with center. And this means that C of H coincides with its center. Therefore, it is abelian. Right? So therefore, C of H is abelian. The only thing that is left to prove is that every element from C of H is semisimple. Then C of H will be toral, therefore it will coincide with H, because H is maximum.
Sorry, can you repeat?
Yes.
Since when you were saying that C of H is nilpotent, so it's solvable, and then?
Yes, so therefore C of H is solvable ideal of C of H. This is tautology, but I would like to, to refer to it. Therefore, it's inside radical of C of H. So therefore, we have this. Yes. Okay. So what's left is to prove that every element X. So it is left to prove that every X from C of H is semisimple. Right. So I would like to prove that, so if I take X, decompose it using Jordan decomposition, then Xn is 0. Okay? So let me take add Xn. So C of H is commutative, is abelian. Therefore, add Xn and add Y commute for every Y from C of H. Right? Yeah, by the way, this is semisimple both in C of H and in G, as we agreed. Right. So it means that I can take add X. So this thing is nilpotent, right? It means in some power, it is 0. Then if I take this, add X times add Y. It's just multiplication of matrices, of linear transformations. If I take it to some power, n, since they commute, it is add xs to the power n, add y to the power n. Right? So therefore, this thing is also nilpotent. Right? So if my n kills add xs, it also kills add x times add y. Right? So therefore, add x n add y is nilpotent for every y in C of H. Right, but this means, so nilpotent, but this means that the killing form of this in G of x, n, and y is 0. So it's nilpotent as a matrix. In some basis, it's just upper triangular matrix, right? But I take upper triangle. How do I compute killing form? I take product of this and compute the trace. So the trace of upper triangular matrix will be 0. So this is 0 for every y, again, in C of H. But the killing form restricted to C of H is non-degenerate. Restricted to C of H is non-degenerate. It means that xn is 0. And it means that x coincides with its semisimple part. It means that x is semisimple, right? So therefore, we prove that C of H consists of semisimple elements, right? And it's abelian. Therefore, it's toral. It's toral, which contains a maximal toral subalgebra. Therefore, it coincides with its maximal toral subalgebra. Right? And we are done. So let me just write this down to have everything on board. So C of H is toral, and H is inside C of H. And H is maximal toral. Therefore, H equals C of H. Therefore, H is a Cartan subalgebra by definition. And we are done. So we proved at least that Cartan subalgebras exist in every semisimple algebras. Another question, how different they are. So the answer to this question is that they're all conjugate in the sense, the conjugations in the sense of Lie algebra. So they differ by add x, where x is some element in the algebra. But in semisimple, this transformation add x is actually an isomorphism of vector spaces, right? Because center is 0. So therefore, they differ by some isomorphism of vector spaces. In particular, their dimensions coincide. And dimension of Cartan subalgebra is called the rank of G. Okay, so maybe this conjugate part we will skip, but at least we know that we have something to work with.